Welcome to the deep dive. Our mission today is to give you, well, the ultimate shortcut to understanding one of the most foundational areas of organic chemistry,
Carbonyl compounds.
specifically aldehydes and ketones. We are going to try and extract every essential reaction, every preparation method, all the key tests, and the analysis you need all in one sitting.
And the thing is, these compounds are just inescapable. They aren't some dry topic in a textbook. They literally define the world around us.
You mean like flavors and smells?
Exactly. Think of benzaldehyde. That's the complex, classic aroma of almonds. Or citronellal, which gives that sharp, lemony scent that's famously used in mosquito repellents.
And they all share one common feature that makes all that chemistry happen.
That's right.
So that's our journey today. We're going to start with their basic structure, then move into how we make them and how we can reverse that process.
The really fun part, the chemical detective work.
The tests we use to identify them, and we'll finish up with how modern spectroscopy can give us that final confirmation.
Sounds like a plan. So let's start with the absolute core, the carbonyl group itself. It's written as C double bond O, or CO.
And the critical difference between an aldehyde and a ketone is just where that group is located.
It's all about location. In aldehydes, the carbonyl carbon has to be bonded to at least one hydrogen atom.
Which means it's always at the end of the chain, right?
Always. It has to be terminal. And that makes naming them pretty straightforward. You just take the alkane name, you drop the final E, and you add al.
So ethanal, propanol.
Exactly. And because it's always on carbon 1, you don't even need position numbers.
But ketones are different. They're sort of buried in the middle.
That's the perfect way to put it. In ketones, the carbonyl group is attached to two other carbon atoms, so it's always inside the chain somewhere.
And the naming follows a similar pattern.
It does. Drop the E, add 1. But here, the position numbers are absolutely essential once the chain gets longer than butanone. You have to say, is it pentan 1 or is it pentan 3-1?
You have to specify its address.
Pers-
And if we link this back to what we know about alcohols, this all clicks into place. Aldehydes come from oxidizing primary alcohols.
And ketones come from oxidizing secondary alcohols.
So let's use that as a jumping off point. How do we prepare them using oxidation?
Okay, so our main tool for this job, generally, is potassium dichromate solution. We acidify it with some dilute sulfuric acid to get it going.
And for anyone in the lab, there's a very obvious visual cue that the reaction is actually working.
Oh yeah, it's a great one. The solution starts off this bright orange color from the dichromate ions. As the reaction proceeds, it turns into this lovely murky green color from the chromium ions.
So that color change tells you your oxidizing agent is doing its job. But the procedure for making an aldehyde is famously delicate. Why is that specific distillation step so critical? What happens if you just leave it in the flask?
This really gets to the heart of the reactivity. When you oxidize a primary alcohol, you get an aldehyde. But the problem is, aldehydes are themselves really easy to oxidize.
Ah,
So if you leave it sitting in that hot, oxidizing mixture, it's not going to stay an aldehyde for long. It'll just keep reacting and turn into a carboxylic acid.
so it's a race against time, basically.
It is. Luckily, aldehydes have a lower boiling point than the starting alcohol. So you heat it all very gently, and you distill the aldehyde off the very moment it's made. You snatch it out of there before it can react further.
That makes sense. Now, ketones, they're a bit more robust, I take it.
Much more forgiving. You use the same reagents as secondary alcohol, but you can just heat the whole mixture under reflux. Let it run.
Why the difference?
Because ketones are tough. They resist further oxidation. So you don't need that frantic immediate distillation. You could just let the reaction go to completion.
Okay, so now we know how to make them. Let's flip the script and talk about undoing that. Let's talk about reduction, turning them back into alcohols.
And the outcome here is very predictable. You reduce an aldehyde, you get a primary alcohol back.
And reduce a ketone.
You get a secondary alcohol. In the equations, we just use the symbol H to stand in for a hydrogen atom coming from the reducing agent.
And speaking of those agents, there are two main players we need to know, sort of at different power levels.
That's right. The milder, more common one is sodium tetrahydridoborate, or NaBH. You use it in an aqueous alkaline solution, warm it up, and it does the job nicely.
But if you need more firepower,
Then you bring out the big gun, lithium tetrahydroaluminate, LiAlH.
and this is the one that comes with serious safety warnings. Specifically, it has to be used in a completely dry solvent, like diethyl ether. Why is that so non-negotiable?
Because LiAlH is incredibly reactive. It reacts violently with water. I mean, violently. Even a trace of moisture will destroy the reagent and could be quite dangerous. So the solvent has to be bone dry.
Got it. Okay, let's move on to a totally different kind of reaction. Not oxidation, not reduction, but nucleophilic addition, specifically with hydrogen cyanide.
Yes, and this is all about the polarity of that CO bond. Oxygen is highly electronegative.
It's an electron hog.
It's a total electron hog. So it pulls the bonding electrons towards itself. This gives the oxygen a partial negative charge, and most importantly, it leaves the carbonyl carbon with a partial positive charge. It's electron deficient.
And that makes it a target, a big flashing target for anything that's rich in electrons, a nucleophile.
Precisely.
But this reaction seems pretty intense. You're generating toxic hydrogen cyanide right there in the flask from potassium cyanide and acid. What's the synthetic payoff? Why would chemists do this?
The payoff is huge. This is one of the best, most reliable ways to make a carbon chain one carbon atom longer.
Ah, you're adding a carbon.
You're adding a whole new carbon atom in the form of a nitrile group, CEN. The product is called a 2-hydroxynitrile. And what's more, you can then easily take that nitrile group and hydrolyze it with acid to form a carboxylic acid. It's an incredibly powerful tool for synthesis.
So let's just trace the mechanism verbally. The nucleophile is the cyanide ion, CNI. What happens first?
Right. So step one. The cyanide ion, where the negative charge is on the carbon, by the way, attacks that partially positive carbonyl carbon.
Okay.
That attack forces the electrons in the pi bond of the CO to jump up entirely onto the oxygen atom.
Creating a negative charge on the oxygen.
Right, a very reactive, negatively charged intermediate. Then step two is almost instantaneous. That negative oxygen grabs a hydrogen ion and 8 from the surrounding solution.
And that stabilizes everything.
And you get your final product, the 2-hydroxynitrile. And because of how it forms, that HOH group is always on the carbon right next door to the nitrile group.
Okay, that's brilliant. So we've built them, we've broken them, we've added to them. Now let's do the detective work. How do we test for them? We need, what, 2 kinds of tests?
Exactly. First, a general test just to see if you have a carbonyl group at all. And second, a test to tell an aldehyde apart from a ketone.
Let's start with the general one. How do we just confirm the CO group is there?
For that, we use a reagent called 2,4,4-dinitrophenylhydrazine. It's a bit of a mouthful, so we just say 2,4,4-diandrophenylhydrazine. It's a bit of a mouthful, so we just say 2,4,4-DNPH.
And what's the positive result?
If you have an aldehyde or a ketone, you mix it with 2,4-DNPH, and you immediately get this deep, vibrant orange precipitate. It's unmistakable.
So beyond just a simple yes or no, how do chemists use that orange solid?
That's the clever part. You can filter off that orange precipitate, purify it, and then measure its melting point.
Ah, and every derivative has a unique melting point.
Exactly. Every single aldehyde and ketone forms a derivative with a slightly different, very precise melting point. So you can look up your value on a data table and identify the exact compound you started with. It's like chemical fingerprinting.
That's brilliant. But that test works for both. So what's the fundamental difference we can exploit to tell an aldehyde from a ketone?
It comes back to what we said earlier. Aldehydes are easy to oxidize.
And ketones are not.
Ketones are tough. So we just need a mild oxidizing agent, something strong enough to react with the aldehyde, but too weak to bother the ketone.
Okay, let's look at the first one. Tollens reagent.
Tollens is basically an ammoniacal silver nitrate solution. The silver ions, agoria, are the mild oxidizer.
And what do we see?
If you warm it with an aldehyde, the aldehyde gets oxidized and the silver ions get reduced to actual silver metal.
The silver mirror.
The famous silver mirror. You get this beautiful shiny coating of silver on the inside of the test tube. With a ketone, you get nothing. The solution stays clear.
Fantastic. And the other option is Fehling's solution.
Fehling's is an alkaline solution that contains these bright blue copper ions, Qi.
And with an aldehyde.
You warm it up and the aldehyde reduces the blue Q ions to copper ions, which form copper iodide. This stuff is insoluble and it's a brick red or orange color.
So you go from a clear blue solution to this opaque reddish precipitate.
Exactly. That's your positive test. And again, with the ketone, absolutely no change. The solution just stays blue.
Perfect. Now let's shift to a very, very specific test. The iodoform test. This one isn't general at all, is it? It's looking for a very particular piece of a molecule.
That's right. This test is designed to find one thing, the Chaseco group. We call that a methyl ketone.
So if your molecule has that group, what happens?
You warm the compound with some alkaline aqueous iodine, and the key observation, the positive result, is the formation of a brilliant yellow precipitate.
And that's the tri-iodomethane or iodoform.
That's the one, CHA.
Now, there's a really important exception here. there is one aldehyde that gives a positive result.
Yes, and it's ethanol.
Why is ethanol the outlier?
It's simply because its structure is Chechesh. It's the only aldehyde that actually contains the required K-show structural unit, so it passes the test. All the other aldehydes fail.
That specificity is really useful, and you mentioned it can also be used indirectly for some alcohols.
Correct. It can identify a secondary alcohol that has this HAs group.
How does that work?
Well, the alkaline iodine is also an oxidizing agent, so the first thing it does is oxidize that specific alcohol group into a methyl ketone.
Ah, so it creates the very group the test is looking for.
Exactly. And then in the same pot, that newly formed methyl ketone immediately undergoes the iodoform reaction to give you that telltale yellow precipitate. It's a neat two-step deduction.
Amazing. Okay, let's wrap up our analytical toolkit with infrared spectroscopy. The final confirmation. What are we actually looking at on an IR spectrum?
With IR, you're essentially shining infrared radiation on your sample,
Mm-hmm.
and the bonds in the molecule absorb some of that energy and start to vibrate. They stretch and bend. We measure which frequencies or wave numbers are absorbed.
And different functional groups vibrate at different predictable frequencies.
Precisely. It allows us to spot the functional groups.
So for our carbonyl compounds, what is the dead giveaway? What's the signal we're searching for?
You are looking for the C double bond O stretch. This bond gives a very strong and very characteristically sharp peak on the spectrum,
And whereabouts do we find it?
typically in the range of about 1670 to 1750 inverse centimeters.
And you said the sharpness is key. That's a great detail because it contrasts so strongly with other common peaks, doesn't it? Like for an alcohol.
Absolutely.
Yeah.
The OH bond in an alcohol also has a strong peak, but it's way up around 3200 to 3600, and it's always very broad.
Why is it so broad?
Because of hydrogen bonding between the molecules, it smears the signal out. So you have this big, broad OH peak versus the intense, sharp CO spike. They're impossible to confuse.
So if you were trying to distinguish between, say, butanone and butanol, you'd look for that sharp spike around 1700 for the ketone or the big, broad lump higher up for the alcohol.
That's exactly how it's used.
And that brings our deep dive to a close. We've covered, well, everything from their basic definitions, the tricky preparation of aldehydes, the powerful reduction methods, that clever chain lengthening reaction.
And then all the tests, the
Yeah.
broad carbonyl test, the specific Tollens and Fehling's test to tell them apart, and the super specific iodoform test. It's a complete toolkit.
So for everyone listening, now that you know the pathways forward and backward and the tests to confirm each step, consider this. If you successfully reduced a methyl ketone, let's say propanone, back to its secondary alcohol, propan-2-ol, how would the results of the mild oxidation tests like Tollens or Fehling's and the structural iodoform test change from what you started with to what you finished with? How could you use those changes to prove you made what you think you made?
A great question. It forces you to connect all the dots we've talked about.
Absolutely. Thank you for joining us on this deep dive. We hope you feel thoroughly well informed.